Hello, my name is Sawyer Schmidt, and this is a presentation about calcium citrate as an effector of glycogen phosphorylase B. I use a spectrophotometer to read the absorbance of different assays to determine whether calcium citrate is an activator or inhibitor of glycogen phosphorylase B. So first, a little background on glycogen phosphorylase. It exists in two forms, phosphorylase A, which is the active form, and phosphorylase B, the inactive form. So the interconversion between these forms is regulated by reversible phosphorylation. Phosphorylase B kinase activates phosphorylase B by phosphorylating a specific serine residue, thus converting it into phosphorylase A. In contrast, protein phosphorylase 1 deactivates phosphorylase A by removing this phosphate group, reverting it back to phosphorylase B. So this is important for glycogen breakdown, which is the process by which stored glycogen is mobilized to release glucose for energy. And once activated, glycogen phosphorylase catalyzes the phosphorylate cleavage of alpha-1,4 glycosidic bonds using inorganic phosphate, which releases glucose 1-phosphate. And then each cleavage shortens the glycogen molecule by one glucose unit, enabling a stepwise degradation of glycogen as needed. So we first completed assays to determine how different concentrations of inorganic phosphate react by measuring their absorbance at 600 nanometers. This data is shown in this graph here, and then we applied this to the rest of our assays. So the first effector we tested was AMP, which is a known activator. We found that as the concentration of AMP increased, as did the rate of reaction. Interestingly, though, um, the reaction proceeded at the same rates for 1, 2, and 4 millimolars of AMP. Next, we tested nicotinamide, which is a known inhibitor. We found that as the concentration of nicotinamide increased, the Km also increased. So that is consistent with the competitive inhibitor, which competes with the substrate to bind to the active site of glycogen phosphorylase. And then finally, I tested 10 milligrams per millimole and 2.5 milligrams per millimole of calcium citrate in different assays with 4 millimole AMP and zero point 0.5 millimole AMP. So the Vmaxes were very similar in the 4 and zero point 0.5 millimole AMP for each of the amounts of calcium citrate added, and overall did not change very much. The Km values, however, did vary more, and they were higher for the 10 milligrams per millimole of calcium citrate than they were for the 2.5. However, I was able to conclude that there was not enough difference overall to consider calcium citrate as an activator nor inhibitor of glycogen phosphorylase B, just because the differences were not too great um, in general. Um, and then in the future, I'd want to study the effects of calcium citrate, of calcium and citrate independently on glycogen phosphorylase B to see how they would affect it without the presence of the other. And then I would also want to repeat this experiment to ensure that the conclusions I made are accurate. Um, so to summarize, if we were able to improve that AMP was an activator and nicotinamide is an inhibitor of glycogen phosphorylase B, calcium citrate was shown to be neither an activator nor an inhibitor of glycogen phosphorylase B. However, there were some outliers absorbed, so repeating the experiment as said in the future directions could lead to more accurate data and a more accurate conclusion about how calcium citrate truly affects glycogen phosphorylase B.